Hi, I'm Navish Kapche, a student from Federation University, Australia. I'm going to present my research about radiation modeling and hydrodynamic analysis of particle solar receivers. I did this research in collaboration with my project supervisor, Dr. Apur Kumar. First of all, I would like to introduce a brief introduction to you about CSP systems, which stands for Concentrated Solar Power Systems. These systems are capable of higher solar energy absorption from solar irradiation than conventional solar receivers. Usually, they can reach up to 1000 degrees if we use certain ceramic particles as the heat transfer media. As an example, this figure represents a CSP power tower system. Usually the receiver is located on top of the tower and heliostat field located on the ground concentrate the solar radiation to the receiver through an aperture. Usually yeah, molten salt, solid particles, thermal soil, oil and gases used as the heat transfer media for these systems. The energy absorbed by these systems can be utilized to generate the electrical and mechanical power. These are some common CSP technologies available. The most common types are parabolic trough, power tower systems, and parabolic dish systems. In this research, I focused on power tower systems. When it comes to power tower systems, there are several particle flow systems as well. In this research, I considered free-falling particles under gravity. So the ceramic particles will flow into the receiver through this hopper while creating a particle curtain. The concentrated solar power will be absorbed by the particles in the curtain. These are the research gaps that I'm going to discuss within this research. There are a limited number of studies carried out to analyze the particle hydrodynamics and radiation characteristics with respect to the particle size distribution within the curtain. Most studies conducted by considering monodisperse size particles only. There are limited CFD analysis has been conducted to model radiation of the particle curtains related to polydisperse size particles. As per summary, the main research objectives are to design a particle solar receiver model and examine the particle size distribution behavior and also analyze the radiation characteristics and hydrodynamic variations of the particle curtain against different particle mass flow rates. This is the geometry of the numerical model that I have developed using ANSYS Fluent. This 2D structure represents the receiver cavity in two-dimensional space. Ceramic particles fall into the receiver cavity from the inlet at the top of the tower and falls towards the bottom of the cavity under the gravity. I have assigned three boundary conditions as inlet, pressure outlet, and back wall. Um, and the width of the inlet slot was taken as 5.5 millimeter. Concentrated solar radiation comes through the aperture located nearby this side of the pressure outlet, and it will absorb by the particle curtain within this area. I have generated the mesh as follows. You can see that I have divided the mesh areas into 5 different surface areas. Because mesh was generated based on the size of the particle distributions within the receiver cavity. You will see that uh, within this research, the finer particles will be uh, moved towards the core of the receiver, and the larger particle diameters will be moved towards the periphery of the particle curtain. That's why I created finer mesh towards the uh, cavity area of the receiver. I utilized the Eulerian multiphase model for the numerical model that I have developed using ANSYS. I have assigned two phases within the receiver cavity. I used gas as the primary phase and ceramic particles are assigned as the secondary phase. The particle material selected as HSP ceramic, and specifically for the validation of the model, I used the specific initial volume, inlet volume fractions and particle diameters to validate the model with previous experimental data obtained by literature studies. I used experimental and simulated data obtained by Ho and his team to validate my model. The dataset that they obtained with 6.35 millimeter aperture have utilized for this validation. As they did, I have recorded the velocities of the particles at three different height levels from the inlet at 2.79 kg per second mass flow rate. According to this comparison graph, it indicates that the results are within 5% tolerance with this previous experimental data. To model the particle size distribution, I used Gaussian probability density function to split the range of the particle size within the curtain to 5 different equal area bands. For this experiment, mean particle diameter is used as 280 micrometer, and particle diameter range was selected from 10 to 550 micrometer diameter. Using Gaussian PDF, I obtained these mean particle diameters in each area band. So for this research, I had simulated the model for three different mass flow rates. They are 2 kg per second, 4 and 6 kg per second mass flow rate. First of all, this slide shows the velocity contours obtained for each mean particle diameter at 2 kg per second mass flow rate. But when it comes to this slower mass flow rate, I got almost equal velocity contours for each band. But I have recorded average velocities of the particles within the curtain at three different heights by assigning cutoff volume fractions. This graph represents the average velocity of the particle diameter versus distance from inlet. This result indicates that the smallest particles achieved higher velocities within the curtain than the large particles. These plots show that the volume fraction of each particle diameter phase versus distance across the particle curtain. As you can see here, the width of the particle curtain decreased when the particle reached towards the bottom of the receiver. And another thing to notice is that you can see here the larger particles tends to stay within the periphery of the curtain, while smaller diameter particles tends to stay within the core of the particle curtain. These plots represents the particle curtain widths at different height levels from the inlet with respect to the each size band. As I explained previously, larger particles have the widest curtain, while smaller particles has a smaller curtain width, and they stays within the core of the curtain. These are the velocity contours obtained for each particle diameter bands at 4 kg per second mass flow rate. You can see that 280 micrometer diameter particles reaching higher velocities since they have the highest particle volume fraction within the curtain. Then same as previous, when we plot the average velocity data obtained after volume fraction cutoff versus distance from the inlet, it shows that even they start with same velocity, when they reach up to 0.85 meter in the bottom, smaller particles reach slightly higher velocities than other particles. The actual reason behind this is because since the smaller particles are stays within the core of the curtain, they can reach higher velocities. The larger particles move towards the outer area of the curtain, and these particles has to undergo through the drag from air. This makes larger particles to slow down. As same as in previous case, you can see that smaller particles has smaller curtain widths and stays within the periphery of stay within the core of the curtain, and larger particles has larger particle curtain widths and move towards the periphery. But when we compare it with the 2 kg per second mass flow rate scenario, the width difference get decreased. As I mentioned previously, you can see that um, how the width difference reduced than slower mass flow rates. The graphs also presents about the scenario and shows how the particle curtain width varies with respect to each particle diameter at each height levels. Finally, these are the velocity contours obtained at 6 kg per second mass flow rate. You can see that the width of the particle curtain has reduced than the previous mass flow rates. When we plot the average velocity data at each height from the inlet, it shows that almost every particle diameter has same average velocities from the top of the receiver to bottom of the receiver. We can identify the reason behind that from these plots, because as you can see here, um, since the particle curtain width has reduced than previous cases, every particle diameter nearly stays at the periphery of the curtain, and they they have to face the drag from the air equally within this thin curtain. Due to this, each and every particle diameter shows nearly equal velocities across the distance. Here also you can see that at each height level, most of particles has quite similar particle curtain width, as I mentioned previously. Finally, I used discrete ordinate radiation model in ANSYS Fluent to determine the radiation absorption by the curtain at each mass flow rates. I use this opacity equation to calculate the opacity of the curtain along the receiver height, which is 1 minus transmissibility, and we can evaluate the transmissibility in this equation. And I use this incoming beam radiation for my simulation as well. So you can see that opacity of the curtain is reduced when the curtain reach from top of the receiver to the bottom, especially with 2 kg per second mass flow rate. Also opacity has reduced when we reduce the mass flow rate as well, since we know that if the opacity of the particle curtain is reduced, the radiation absorption by the curtain also reduced. This clearly shows that we can obtain higher radiation absorption when we increase the mass flow rates of the particles. These are some references that I use for this presentation. Thank you.